Okay, today I want to talk about Ampere's law. The basic idea is very similar to Gauss's law. When you have to go through and integrate the electric field for several different charges, that was a lot of work. The law of Biot and Savart, Biot-Savart law, is a lot of work as well. So we try to simplify it with Ampere's law. It's not the same thing as Gauss's law for magnetism, but it's the same idea where you're looking at what's inside a particular loop as opposed to a surface to figure out what the magnetic field is. So now, Ampere's law says basically this. Ampere's law. Okay, says integral, that little circle on there again, we'll talk about that in a second, of v dot ds is equal to mu dot I enclosed. Okay, that ENC is enclosed. All right, so now, what does this mean right here? This means that it's a closed loop. And that little circle there means it's a closed loop. So we're going to integrate about something that's a closed loop. When we did it for Gauss's law, it was a closed surface, so this is a little bit different. Okay, but either way, it has to be closed. The ENC here means all the net current that is inside our loop, and it's called an Amperian loop. So now, let's just look at a general example here. Let's just say I have three currents. One that's coming out of the board here, another one that's going into the board, and another one here is coming out. Oh, so I1, I2, and I3. Okay. So now I'm going to make a general Gaussian, Amperian loop. It has to be differentiable, which means it has to be smooth. Okay, no sharp kinks or anything like that. Actually, I don't even think it has to. Well, yeah. So now, this contains the current enclosed is I2 and I3. But when I have to give this a direction, okay, so that's my direction. Now, when we make positive here, okay, typically positive is going to be counterclockwise. Usually we would want out of the board to be positive and in the board to be negative. So counterclockwise is our positive. And so we would say, so if out of the board is positive, I3 would be positive, I2 would be negative because I2 is going in. So I enclosed, remember it's a net current, equal I3 minus I2. And that's our I enclosed. Now, let's talk about the B. And I1 doesn't come into play here because I1 is not inside our Amperian loop. So now, let's just say that my magnetic field, let's just say my magnetic field goes in that direction. And ds is always tangent to our path. This is going to be our ds. And this is our b, and that's going to be theta. All right, so now we can rewrite b dot ds as b cosine theta ds. Or the portion of b that's in the direction of ds. So that would be, we're looking at it like that, we'd be looking at this portion of b, okay, this component of b along the ds direction. So whenever we do that, we have to look at cosine. So now, when I look back at my Amperian, my Ampere's law, okay, B dot ds, B is the direction of the magnetic field at this point. ds is our loop. Okay, dot product gives you the cosine, and the I enclosed is going to be what's inside our Amperian loop. Now, one thing that's important to note, this B has to do with the magnetic field at this location. Magnetic field at this location is caused by this and by I1, which is outside our Amperian loop. You might say that's odd that I have something that's not not inside of our Amperian loop, causing part of the magnetic field that we can solve for. Okay? Well, here's the thing. I1 here, okay, along this loop, okay, the magnetic field due to I1, okay, that's coming out of the board. Here, my magnetic field at this location due to this is going to go in this direction, and my loop also goes in that direction. So you'd have some sort of positive part there. Over here, though, again, it's the magnetic field would be going in this direction, okay, off in that direction, while my Amperian loop goes in this direction, so I get a negative result. Okay? So I get a negative result here. Here I get a positive result. So what happens is, what this does as part of our calculation cancels out. Okay? So now, the way that I'm functionally going to use this typically is that this is going to be the integral of b cosine theta ds, and then u naught, and still I enclosed. Okay, however that works out. So now, but I'm typically going to call it just b cosine theta, and most of the time we want that cosine theta to disappear. It's either going to give us 0 or 1. So now, let's talk about, and in this case here, okay, in this specific case, I would say my integral, using Gauss's law, would be b cos theta ds is equal to u naught I3 minus I2. Now, I don't have enough information to do this part, especially with the ds. B is going to vary along that. So typically, like Gauss's law, where we don't want the electric field to vary along our Gaussian surface, we don't want the magnetic field to vary along our Amperian surface. Okay, or at least it's either going to be positive, negative, positive value or negative value that go together, or 0. Okay, so now let's take a look at how this is useful. Okay. Now, we did a long straight wire, and it actually took a little bit of work to get through that. So now, let's take a look at a long straight wire, and see if we can't simplify this down, and see how Gauss's law makes this easier. So now, I have a wire with a current I going in this direction. Now, I want to know what the magnetic field is at a point. I'm going to just put it right here, okay, a distance r away from my wire. Okay, I'm using a little r there. Okay, so now here's the thing. The ds, okay, ds is always parallel to the Amperian loop. So ds points in that direction. Well, we already know that, according to right-hand rule, that it's going to go around in this direction. So this is wrapping around in the same direction. Our loop here is wrapping around in the same direction as magnetic field. So ds points in that direction, and we know that b also points in that direction. So now, the angle between b and ds is 0. Cosine of 0 is 1. B is constant all along this loop. So now I can do Gauss's law, Ampere's law for this. This is going to be B dot ds. Dot product gives us 1 equals mu naught. I enclosed is just that current I. Okay, so this off. So now, cosine gives us 1, B is constant. I get the closed loop of ds, mu naught I. So as I go around this loop, the distance that I travel around this loop is going to be the circumference, which is 2 pi r. Equals mu naught I. So B is equal to mu naught I over 2 pi r, which is what we had before. This is much simpler than what we did for when we did it with Bios of R. Now, here's the thing. I can do a much more complicated problem than I could with Bios of R. I can look at the magnetic field inside of a wire. So let's just say that I have a wire here. I'm going to look at the cross-section of this wire. Okay, I'm going to actually make it a little bit bigger. Okay. Now, I'm going to say that this wire has a current coming out of the page, and this wire has a radius capital R. Now, I want to know what the magnetic field is, a distance little r away, and I'm going to put it at here. So now, R is going to go, so I want to know, this is my full wire. I want to know what the magnetic field is right here inside this wire. I couldn't do this with, well, I could do it with Bios of R. I couldn't do it easily with Bios of R. So now, let's take a look at what happens here. Okay, again, ds and B point in the same direction. So this is going to be B dot ds is equal to mu naught I. Yeah, I'm going to say it carries current I. Okay, I enclosed. Now, I enclosed does not equal I, because current is carried outside here too. So I only look at the current that's inside this surface, inside the green here. So just as before, this becomes B times 2 pi, and I'm going over little r, okay, just as I did before, is equal to mu naught I enclosed. Let's take a quick look. I enclosed is going to be the ratio of I that's for the whole thing, okay, the part that's inside here to the part that's outside. So that's going to be this area compared to this area. The inside area is pi little r squared. Area of the whole thing is pi big R squared. So I want the area of what's inside here to the area of the whole thing. That's going to give me what I enclosed is. Pi is dropped. So I enclosed will equal I little r squared over big R squared. So now I plug that in. I little r squared over big R squared. One of the r's drops. So I'm left with my magnetic field is equal to mu naught I. I'm going to hold this r off to the side here. Over 2 pi r squared. All of these are constants. The only thing that's not a constant necessarily is r. So B is a function of r, inside is a linear function of r. So if I was going to graph this, think I'm running out of space there. Going off the page. So if I graph this, B versus R, okay, my magnetic field would increase until R equaled R. Okay, this is B being proportional to R. In fact, at this point, B would equal mu naught. Figure it out, see if you can figure it out before I write it all down. You can pause it if you need to. Mu naught I over 2 pi big R. That's what it would be right there. Then this would drop off, and B is proportional to 1 over R. So this just gives us a picture of what the magnetic field looks like. This is inside the wire, this is outside the wire. All right, last two things that we need to talk about are solenoids and toroids. So now, a solenoid is something where, and this is where we get our, essentially an electromagnet from. Okay, solenoids are also in cars. They help with the starter. And we'll talk about some of the uses for this as we go on. But let's, essentially, for right now, we'll just say that it has we can create a very strong magnetic field. So now, let's just say that I have some sort of core here with a wire wrapped around it. Okay. Come down there. Okay, so now we're going to have the current go in this direction. So the current is going up on the front side. If you looked in the back, the current would be going down. Now, a few things. Imagine each point on this wire going where the current would be going up right here. Our fingers wrap around in the direction of the magnetic field. So in front here, the current goes up, magnetic field in this core goes that way. Over here, okay, it's going down, behind it, it's going down. So now this is behind the magnetic field. Behind our bar here, okay, magnetic field is also going this way. When I'm on top, okay, current is going into the page. Magnetic field swings around over in this direction. Magnetic field for this whole thing points. All these wires work together to produce a magnetic field inside here that points like that. Okay? And we have a magnetic field that loops in. Okay? All of these have to loop around eventually. But the idea is that inside that bar, you get a very strong magnetic field. Okay? So if I looked at this in cross-section, okay, where I had our solenoid here, okay, if I cut this across, you're going to have, okay, with the wires here, the current's going into the page up here, so I've got X's up top, and I have dots down below. So now, if I did an Amperian loop here, okay, so this will be A, B, C, D. So now, what I will do is say, all right, B dot ds is equal to u dot I, and I just put a little I here, I enclosed. Okay. So now B here, so I have to break this up. I have from A to B, B dot ds, plus, and notice that this isn't a loop anymore. We're breaking it up into 4 different sections. From B to C, B dot ds from C to D and from D to A of B dot ds. Now, I didn't bother writing the rest of those in, and you'll see why in a second. Okay, we said that the magnetic field was going in this direction. So my magnetic field goes in that direction. If it's going in that direction, okay, from A to B goes that direction. Okay, so we're going to wind up with a negative here. Magnetic field is constant in this area. So now I can rewrite this. I'll get negative B, okay, dot ds. So that's going to be from A to B. Let's just call this H. Okay. Now, here's the thing. Magnetic field's going this way, and B and C and A and D, okay, those are going in 90 degrees. So A to D goes to 0, B to C goes to 0. Outside a solenoid, outside a perfect solenoid, we see that the magnetic field is 0. So the only portion, so this goes to 0 as well. So now, the only thing that's creating a magnetic field is, what we're integrating over is that area right there. ds is just the distance, and we get a negative here. So now, that's mu naught I enclosed. Now, I enclosed, this has a certain number of turns per unit length. So I'm going to say that this solenoid has n, which is the number of turns per unit length. Little n. Okay. So now, if I want n, okay, I'm not looking at the whole length. If I'm looking for the number, the current here, little n is the number of turns per unit length. H is my length. So this is going to be mu naught. The current here is going to be n, h, that's the turns per unit length, times the current I. The h's drop. So, and this current was negative because it's going into the board. Out of the board is positive. So the negatives will now drop. So my magnetic field is equal to mu naught n I. All right, I have students going to come in for some extra help for their quarterly, so I'm going to stop there. We'll talk about toroids in class.
If gap follows, please call 1205.